Today on How It's Made. Pasta dies. Blueberries. Composting toilets. And surge arresters. Industrial pasta machines produce noodles by extruding dough through a die. The die has holes in it, which are shaped to produce a specific type of pasta. As the dough comes through the holes in a continuous stream, a knife cuts the pasta to the correct length. This industrial pasta die produces fusilli, up to 1.5 tons of it per hour. And this is just a mid-sized die. The largest ones can produce 4 tons of pasta per hour. The die block is made of a bronze-aluminum alloy. A computer-guided machine drills holes for inserts through which the pasta dough will be extruded. The front of the block is then chrome-plated to protect against the sharp knife that cuts the extruded pasta off the die. The next step is to make inserts that go in the holes in the block. An insert is comprised of male and female parts and a non-stick plastic lining. A computer-guided mill cuts the linings from a plate of non-stick plastic. Another computer-guided mill machines the female part of the inserts in a more than 1/4 inch thick brass plate. Then, a worker places a lining in each female part. He taps it into position with a mallet and punch. The plate then goes back on the mill, which cuts an extrusion slot in the lining. The slot shape determines the pasta shape. A mill machines the male part of the inserts in another brass plate. A worker detaches the male parts from the plate with a punch and mallet. He detaches the lined female parts the same way. Then he assembles the male and female parts by forcing one onto the other with the help of a steel punch. He finishes the die insert by cutting off the protruding excess plastic with a blade, so that the lining is flush with the top. The factory makes die inserts in thousands of different shapes, some standard, others in the client's custom-made pasta shape. This computer-guided lathe makes brass locking rings which will secure the inserts in the block. Now, final assembly begins. A worker places the block face down and from the back drops an insert top first into each hole. Next, he places a locking ring in each hole. Then, with a hydraulic press and punch, he forces down each locking ring to within approximately 1 millimeter of the insert underneath. In this position, the ring holds the insert in the hole, but doesn't prevent it from spinning within the hole. The next step is to adjust the inserts to make their orientation uniform. He inserts a pin into each insert slot. Then he rotates the pin to rotate the insert. Once the insert orientation is correct, he forces the locking ring down all the way to immobilize the insert. Once he has all the inserts oriented the same way, he sands the chrome-plated front of the die, first with a medium grit disc, then with a fine grit sandpaper. The die surface must be smooth as silk for the knife to slice off the extruded pasta cleanly. He verifies the width of every extrusion slot with a gauge. This ensures every piece of pasta will be the correct thickness. Then, on the back of the finished die, he stamps the manufacturer's name. The die is ready to be mounted on an industrial machine that extrudes dough into perfectly shaped, ready-to-boil pasta. Blueberries are one of nature's healthiest foods. They're low in calories, packed with vitamin C, and full of antioxidants. And freezing blueberries doesn't compromise any of that nutritional value. North and South America grow most of the world's blueberries. The length of the harvest varies by climate. In the South, it spans April to September. Further north, mid-June to mid-August. At this state-of-the-art blueberry farm, a mechanical harvester straddles the row of blueberry plants and shakes the leaves with vibrating fingers. The berries fall to a sloped floor below and roll down into side conveyor belts. The belts dump the berries into onboard bins, which trucks transport from the field to the on-site packing plant. The plant has two separate production lines, one for berries to be shipped out fresh, and this one for berries to be shipped out frozen. Workers empty the bins into a hopper, which feeds the berries onto a conveyor belt. A vibrating conveyor belt then ferries the berries under a blower that suctions up loose leaves and twigs. Then the blueberries tumble down a waterfall. Stones and debris settle in the ledges. The berries land in a wash tank. Most of the ripe ones sink to the bottom, while most of the unripe ones float on top, where workers can easily scoop them out. The berries exit the wash tank with fewer unripe ones among them. The mesh belt vibrates to gently shake off water. Then it runs the berries through the first of two color sorters. The machine's camera is preset to ignore the color blue and detect only green and red. Whenever a green or red berry passes, the camera sends a signal to the computer, identifying its exact location so that one of the 136 air jets blows it off the belt to a collection trough below. The ripe blueberries fly over the top onto a conveyor belt that takes them to the freezer tunnel. The temperature inside is minus 29 degrees Fahrenheit. 5 to 7 minutes later, the berries exit the tunnel frozen solid. Workers perform a final visual inspection. After passing through a metal detector, the berries drop into a pre-programmed scale that weighs out the specific quantity being packaged. Meanwhile, in an on-site lab, government-trained inspectors pull samples off the line every 20 minutes for grading, which they determine by assessing factors such as color, aroma, and defects. The frozen berries go into a freezer until shipped out by freezer truck. The fresh berry production line is similar to the frozen line, minus the wash tank and, of course, the freeze tunnel. However, the color sorters on this line are even more high-tech. Not only are they set to detect red and green berries, but they also have a firmness detector, which by bouncing each berry on a pad, can identify blue ones too soft to have at least a 12-day refrigerated shelf life. Air jets blow those soft berries off the conveyor, so they can be transferred to the frozen berry line. The rest continue to a final visual inspection. The fresh berries are ready for packaging. This electronic fill machine is preset to weigh out the specific quantity they're packaging, in this case nearly 2-pound containers. It drops that quantity of berries into an awaiting plastic container. The final stop on the packaging line is the flat seal machine. It applies a printed plastic film to the top of the container, melting and bonding it to the perimeter without a touch of heat. The film has ventilation holes because fresh berries require air. From here, the containers go off to a refrigerated warehouse to await shipping to the store by refrigerated truck. And provided they remain refrigerated, the blueberries remain fresh and juicy for 10 to 12 days. There's a new John in town. Composting toilets are the greatest thing since indoor plumbing. In fact, they don't need any plumbing at all, so they can go where traditional toilets do not. They are little waste treatment machines. They turn the unpleasant business of sewage into something more agreeable: garden fertilizer. This composting toilet works a bit of magic with sewage. It transforms the solids into compost and makes the liquids disappear. Making this toilet starts with a composting tank. A worker sprays fiberglass into a mold of the tank. Then, he and another member of the team press out air trapped between the fiberglass and mold surface. Once the part cures, a blast of compressed air loosens it from the mold, and he lifts it out. It's a bit ragged around the rim, so they do a basic trim. He drills holes in the tank for installing fittings. Using a pneumatic circular blade, he slices a hole for the compost drawer. And he grinds the rim to precise measurements. He screws two overflow fittings into a threaded hole on the back of the tank. He seals the fittings with epoxy from the other side of the tank wall. This epoxy seal will prevent leaks. Moving down the line, another worker sprays adhesive on the bottom of the composting tank. He presses an aluminum panel to it. This panel will radiate heat from a heating element he installs over it. It will heat the evaporation chamber in the tank to dissipate liquids. He places fiberglass insulation over the heater and encases it with a molded fiberglass cover. He wires the heater and installs a thermostat that will regulate the heat and also shut off the system if the temperature drops below or exceeds the threshold. He turns the composting toilet tank right side up to await further assembly. Meanwhile, another worker assembles the fan for exhausting the evaporated fluids and any odors. He inserts the motor shaft in a hole in the fan door so that it protrudes inside. He then screws the motor to the outside of the door. Next, he assembles the centrifugal blower to the motor shaft. He installs a plastic shroud. It surrounds the fan, protecting the blades and directing airflow. At the next station, a worker prepares the drum in which solid waste will be converted to compost by aerobic decomposition. He fastens a stainless steel screen to an opening in the drum. Liquid waste will drain through this screen and into the evaporation chamber. Once evaporated, the fan will expel it through the vent stack. He now places the drum in the tank. Bearings elevated so it sits just above the evaporation chamber. He fits a plastic top to the tank and screws the two components together. He inserts a metal shaft with gears, engaging them with grooves on the outside of the drum. He inserts the fan into an opening at the back and secures it. He wires the fan to the power source. He installs a cover to protect the wiring, and he connects the shaft to a handle at the front. It rotates the drum to mix the contents and introduce air so that the aerobic microorganisms will thrive. After electrical and other tests, a worker installs the drawer for the finished compost. She fastens a seat to the base with nylon nuts and bolts with caps. She inserts a plastic liner in the bowl, and this completes the composting toilet. By turning human waste into compost, things will eventually end up smelling like roses. Electrical systems are vulnerable to voltage spikes from lightning or switching surges. Surge arresters take over in these high-voltage situations. When lightning strikes, surge arresters handle the fallout. They divert the ensuing power surges to the earth where they won't cause damage. At their core are discs that act as switches. They turn on and off to divert voltage spikes. The discs are known as MOVs, which is short for metal oxide varistors. A worker loops fiberglass strapping onto aluminum end caps to prepare the casing for the MOVs. He places a spacer on one end of the end caps. He then packs numerous MOVs on top, equipping this arrestor to divert a 60,000-volt power surge. He adds more spacers to fill in any gaps, because the MOV stack has to sit tight within the casing. With the stack complete, he loops more fiberglass strapping around the MOVs to complete the casing. He torques a set screw to compress the stack. The set screw also pushes back the end caps. This pulls the fiberglass strapping tighter. He now clamps the surge arrestor assembly between two mandrels. He ties a resin-reinforced thread around the fiberglass loop at one end. He lowers a guard as a safety precaution. The mandrels then spin the surge arrestor module. As a computer-programmed dispenser, winds the thread around it to strengthen it. It creates gaps between the windings. This will allow sparks and fumes to escape in the event of a power overload. With the winding complete, he cuts the end and tucks it under the last winding. He hangs the module on a rack conveyor, which takes it into a chamber. Here, a tank filled with an adhesive promoting solution rises up and immerses the module. This leaves a coating that will help silicone rubber housing bond to the module later. He removes the hook used to hang the module on the rack conveyor and installs mandrels at both ends to be used at a later stage of processing. He sets the module between the rungs of a chain-driven conveyor. It takes it through an oven set at 302 degrees Fahrenheit. This cures the resin in the thread, causing it to harden around the fiberglass strapping. It also preheats the surge arrestor module in preparation for the next process, the molding of the outer housing. Using the mandrels, he locks two of the surge arrestor modules in a platform and slides it under a mold press. A lift takes it to the press. It injects silicone rubber into the mold, and using pressure and heat, it forms insulating jackets around the arrestor modules. The primer coating enhances the adhesion of the silicone rubber to the modules. He clips off unwanted bits of silicone rubber from the molded housing and cleans up the ends with a wire brush. Surge arrestors come in a range of voltage ratings for different electrical systems. He now lubricates the threaded bolt holes in one end. He aligns those holes with the ones on a terminal connector. He bolts the connector to the surge arrestor. He installs a base on the other end. This base will allow the arrestor to be mounted to the ground to send excess voltages to the earth. He now puts the surge arrestor to the test. He connects electrodes to the terminal connector and to the base. He runs different voltages of electricity through the arrestor and confirms that it adequately discharges them. This surge arrestor is now ready to join others on the grid, forming a defense against lightning strikes and power spikes.